So let me skip all that detail about Fourier and directly go to a response spectrum. And in order to introduce this kind of a spectrum, actually what a spectrum is, it is another form of the same acceleration time history, right. So when I say that PGA is a ground motion parameter, I mean that the whole acceleration time history is represented by one number. Although as I have told that that number may not be a very good representative, but at least I just want to somehow give the same information which is given by the whole history by one number. So PGA is a kind of another representation of the same earthquake or ground shaking actually. So similarly, spectrum is also another representation of the same ground shaking. So Fourier spectrum is another representation. So when I say that this is the Fourier spectrum of this earthquake, it means that either you represent that earthquake by this form UG dot dot versus time, or this form, it is same earthquake. Same information is convertible, is converted into another form. One is time domain representation, another is frequency domain representation, right. Time domain representation means that the main variable which the intensity is the function of time actually, and in the frequency domain representation, the intensity or amplitude is the function of frequency, right. So it is telling that different frequencies have different you can say contributions, some have more, some have less. So response spectrum is also another form of the same acceleration time history. Think of it as another representation of the same graph, but a more meaningful representation. So in order to introduce that representation, let me go back now to the same single degree of freedom system concept. Since you have already gone through the structural dynamics course, so I will take that liberty. So I will just quickly go through that introductory slides. Let us say that you have a single degree of freedom system with some mass and k and a damping constant c, which is actually convertible into xi. Xi and c are convertible, so either c or xi, and it is subjected to an earthquake UG dot dot function of time, right. So that UG dot dot is given, it is some past earthquake, let us say. So UG dot dot versus time, obviously it will be in the form of numeric data, a text file which contains thousands of data points. At each time interval it have the ground acceleration value. So this will be the equation of motion for that single degree of freedom system, right. We can also convert that equation into another form by dividing with m on both sides and converting c into xi, right. So this is another form of the same equation. Either I write the first one or second one, same thing, mass is cancelled out. Now this equation tells us that for any given UG dot dot, from structure side you require just two properties to solve that equation. One is the time period of the structure, which is actually omega, can be converted into omega, and other is the xi value. So the effect of mass and stiffness is combined in the omega value or time period, right. So ultimately I can say that when I solve this equation for any earthquake, it will be obviously the function of time, the responses, displacement, velocity and acceleration of that mass will be the function of time, but from structure side it only require two things other than the earthquake itself. It requires the time period of the structure, capital T, and xi of the structure, right. So if xi is kept constant, let us say 5% for one structure or all structures, if I fix xi equal to 5%, I can say that the response quantities, acceleration, velocity, displacement, they are the function of structural time period for a given earthquake, right. So if an earthquake is given, I can have just time period from the structure side, put it in this equation, if xi is fixed quantity, let us say 5%, right. So I can solve this equation for different time periods, which will each of them will represent a different single degree of freedom system. Let's say a structure having a mass m equal to 1 kg and stiffness equal to 1 Newton per meter, the omega will be 1 and there will be some time period corresponding to that omega. I can convert that, right. So, real structures have a time period, real civil engineering structures may have a time period in this range starting from very low number like 0.01 second up till maybe 4 second or 5 second or 6 second. This is the normal range of the first mode's time period of real civil engineering structures, right. For example, if I represent a 40-story building by a single degree of freedom system, lump all of its mass as a single degree of freedom system, its time period will be around 4 seconds, right. And this can be confirmed by this idea that the first mode time period of that building, in which the structure will be swaying only in only one mode, is around 4 seconds, right. So, what I can do is that I can put a different t every time in this equation for the same earthquake and fix damping ratio 5%, let us say, and every time I pick the response quantities for this mass, because this mass will have a response u function of time, u dot function of time, response velocity, and then response acceleration also u double dot function of time, right. So, the response spectrum curve means that I run this equation for maybe hundreds of times, every time with a different time period going in that equation with one fixed damping value, and every time when I run that single degree of freedom, I extract the peak value of response, maximum u dot, maximum u double dot, which is experienced by the structure, by the single degree of freedom systems as a result of that earthquake, when applied by that earthquake, right. So, I can plot ultimately this kind of a representation where the time period of the single degree of freedom system is on the x axis and the peak value of response, which is extracted every time by changing time periods and running that equation again and again, that peak response is on y axis, right. So, let us say that I do that exercise, that fixing xi equal to 0.05 and omega is changing such that the time period starts from 0.01 second on one end and ends at 4 second on the other end, right. And every time when I fix one time period, I run that equation and I calculate the u of t and I pick its peak number. So, ultimately the max of u can be plotted on y axis, because each of the single degree of freedom system analysis will give me one point on this graph. Let us say I fix t equal to 1 second, I put that in equation. Actually 1 second is representing around 10-story building, for example. So, I run that equation for t equal to 1 second, xi equal to 5%, and I calculate u of t and pick the peak number from that. This will give me one number on that graph corresponding to 1 second. Similarly, for 0.5 second, I take the maximum, or 1.5 second or 2 second. So, I get all these points and ultimately join them and make a curve. That curve will directly tell me the maximum response experienced by all possible single degree of freedom systems when that earthquake will occur, right. So, it is another representation of the same earthquake ug dot dot, but now instead of giving us the information about the ground shaking, it is telling us how the structure or single degree of freedom system will shake, right. So, the response of single degree of freedom system is on y axis, not the ground acceleration on y axis. And similarly, on x axis you do not have the time, you have the time period of the single degree of freedom systems. So, you run hundreds of analysis, actually solve that equation hundreds of times for one earthquake, every time the time period of the structure is changing, right, and ultimately come up with this kind of a graph. This graph can be determined or can be constructed for maximum u or can also be constructed for maximum u dot, maximum response velocity of the single degree of freedom system, and can also be constructed for maximum response acceleration of the single degree of freedom system, right. So, why it is called spectrum? Because it is directly telling you the peak value of response for all possible structures, right. So, for example, if let me go by the slides and I will show you a few examples on the way also. So, what a response spectrum is? It is the plot of maximum response for a ground shaking history, different time period and damping ratio give the response. So, u naught is the maximum value of u throughout the whole history, response history. So, maximum value depends only on two things, because now it is the peak already picked. So, it is no more function of time, it is simply the function of xi value and time period of the structure. Similarly, u dot and u double dot. So, the procedure will be to construct that response spectrum, that you have to solve the single degree of freedom system equation again and again, but every time you change the time period and pick the peak response, and at the end you plot time period at x axis and the peak response, whether it is displacement, velocity, acceleration on y axis, right. So, let us say that I plot such kind of a maximum u on y axis for one particular earthquake. Let us say this was my earthquake, I assumed a xi of 5% and I repeat that exercise. I finally plot that graph between capital T and maximum u. Let us say that curve came out to be like this. Obviously, it will be irregular shaped, because for different time periods the equation of motion will give a different peak response, and depending upon the frequency composition of that earthquake, you will have different peaks in that. So, this kind of a graph will give me the whole picture of the properties of that earthquake in just one graph or one figure. I directly now know that a 10-story building is going to shake this much under that earthquake, and a 20-story building is going to shake this much, right, because I myself know that typically a 10-story building is somewhere here and a 20-story building is somewhere here, and a dam is somewhere here, and a 1-story building is here, a water tank is here, right. So, on the x axis it is not that you have only time period mathematically, actually you think of it as a structure, you can say axis, starting from very low or stiff structure up till very high time period or flexible structure, right. So, as the time period is increasing on x axis, your structures are becoming more flexible. Actually, you are going from low rise buildings to high rise buildings, or short span bridges to long span bridges, right, or low rise towers or structures to very tall towers or structures on the right hand side. So, on this x axis all structures are there for you, right, and in the same figure you now can compare that different structures will experience a different shaking, actually different peak response under the same earthquake, right. So, that is why it is called spectrum of response, that the whole response of the whole time, you can say all types of structures can be seen in one figure, right. Actually, I am having all that discussion for past earthquakes currently, right, for which the history is already available. When we design structures for future earthquakes, what we do is that we set a certain level of hazard which is guided by the building code, and then modify the past ground shaking to match that hazard, right. So, it is not that we directly pick the past earthquake from the databases which are recorded somewhere and then apply them to our structure. We modify them, we treat them, and such that they start representing the future hazard at our site, and that future hazard is dictated or prescribed in the relevant building codes. the previous generation of the PBD was recommending 7 ground shaking, but now they changed to 11. So when you perform dynamic analysis in the performance based design framework, you have to select the 11 ground motions from past recorded data, and that selection process itself requires an expertise about the seismicity of that area. But once you select those ones, then you modify them so that they start representing the hazard level which is expected at your site, and that modification process is guided by the building code, because building code will give you that you should expect this much level of earthquake in future at your site. So you modify those ground shaking such that you amplify them or de-amplify them such that they represent the hazard level of your site, right? So they always will be more than one. So currently I am just showing one example earthquake, that let's say this is my UG dot dot. I can convert it into another representation which is more meaningful. That top representation is telling me how the ground is shaking in that earthquake. This lower graph is telling me how the structures will shake under that earthquake, right? So this is an information in which we are more interested in, how the structure is going to shake. So this figure will tell itself several of the useful information about the earthquake, but we will restrict ourselves in just basic information which is about the spectral parameters, right? So if I plot this graph for the maximum displacement on y-axis for every time period value, this is called the displacement response spectrum. And if I plot for maximum u dot, it will be velocity response spectrum and then also acceleration response spectrum. So acceleration response spectrum will tell you in one figure that different structures are going to get different accelerations, or different structures are going to exhibit different response accelerations under this earthquake, right? And its shape will be different. Typically, as the structures are more flexible, which means as you are going towards right hand side, the maximum displacement increase. So overall the graph is going up. Obviously it will be jaggy, but it is overall going up, and it will saturate at a certain number, and that number will be very close to the peak ground displacement, because after a certain time period the structures become that flexible that the inertia of the structure will govern. They will just keep on standing there, and the ground will be shaking underneath them. So the maximum relative displacement experienced by the structure bottom and top is almost equal to the ground displacement, right? So therefore this graph will go up and up until it saturates almost at the UG naught value, or the maximum ground displacement value, right? But this trend will not be in the acceleration case. In acceleration case it will be like this. If I pick maximum u dot dot on y axis and plot it as the time period function, it will be like this, It will be jaggy obviously, but it will start with certain number, and I may ask you that what should be that number, by the way, for a very low time period, let's say 0.01. It will go up and then again come down, which means that this particular earthquake, for whatever earthquake I plotted that spectrum, there is a range of time periods of single degree of freedom systems which will experience the most acceleration. If your structure is flexible than that, your structure is going to experience less acceleration, and if your structure is stiffer than that, also again less acceleration, right? So there is a range of peak spectral acceleration or peak response accelerations, right? Obviously acceleration response spectrum is more useful for our structural engineering purpose, because we can directly multiply the response acceleration with mass of the structure to convert it into inertial forces, right? So now come to that point that the acceleration response spectrum should start from what value? Any idea or guesses about that? It should be PGA, because just imagine that what will be the kind of a structure which will be located at a very low time period, it will be a very stiff structure. It will be behaving like a rock, right? So that stiff structure will experience an acceleration at its top, which will be almost equal to the ground acceleration, right? It will not have its own dynamics. It will be that stiff, right? So it means that the response spectrum, acceleration response spectrum, starts at the PGA value, but then the structure amplifies that PGA to any number, maybe two times of that PGA or 2.5 times of that PGA. But then as the structure become more flexible, the response acceleration starts reducing, and there comes a time when it is even less than the PGA value, right? So for all these time period ranges, the spectral acceleration, response acceleration, is even less than the peak ground acceleration experienced by that structure. So the structure amplify the effect of acceleration in one time period range, and they de-amplify in another time period range, right? So I can talk on this properties of response spectra for hours, but let's just keep the discussion up till this point, because we will move forward, because I just want to connect it with the future earthquake, right? Connect the response spectra of an existing recorded earthquake with the design spectrum of a future earthquake, which cannot be exactly predicted, right? So this is the same information, so let me skip that. Same thing, that you have an earthquake, you have a single degree of freedom system, you have its time period, you apply that earthquake, calculate its response, pick the peak response, let's say 2.67 inches. So you get 1 point on the response spectrum as a result of solving one single degree of freedom system. So t equal to 0.5 second and 2.67 inches. This is 1 point. So this is 0.5 second time period, and 2.67 is the maximum u which is experienced in that earthquake. Change the time period again. So now actually the single degree of freedom is changed. Its m and k is such that its time period is now 1 second. Again apply the same earthquake, same damping, get a peak response, now it is different, 5.97. Get a new number on that graph, another number on that graph. So repeat that exercise for all intermediate time periods, right? Obviously you have to put that solution of that equation in loop, right? So for all time periods you pick the maximum response and you get all points on that graph, you join them and make this black line. This is the response spectrum. In this case it is displacement response spectrum, but you can also get velocity acceleration response spectra.